Hello and welcome to my Physics Lab 3, Black Holes and Orbits. So as an introduction, this lab is split into two parts, each with a different purpose. The first half involves calculating the mass of a black hole orbited by a planet, by the force of gravity and then working backwards. The second half of the experiment involves developing a model to represent an orbiting craft being influenced by a planet and its orbiting moon, with the ultimate goal of plotting the spacecraft's orbit within the system. So the main ideas is the first one is that the force of gravity acts on a lone orbiting object, and this force can be split into parallel and perpendicular components. Both forces can be calculated independently, and the mass of the black hole can be found by substituting the equation for the perpendicular force into the F-net equation. Second set of main ideas is that the net force acting on the chip is the sum of the attractive gravitational force from the moon and the planet during each iteration, and iterating with the velocity update and then the position update formula enables us to track the orbital motion of the ship and the other bodies. So what we found as a summary was that the mass of the simulated black hole was 1.37456 times 10 negative 34 kilograms. And for the second, although we were not finding the exact initial velocity required to establish a figure-8 orbit, we nonetheless developed an accurate model that shows the effects of both gravitational bodies. So our procedure was pretty straightforward. We first modeled the motion of the planet in circular orbit around the black hole. We then calculated momentum, net force, perpendicular force, and parallel force of the planet. And we substitute values from the mass of the black hole, taking the average of each duration to get a final result. For the second half of the experiment, we set the initial velocity for the spacecraft and determined the force of gravity for each acting on the spacecraft and the moon itself. We can determine the net force of gravity acting on the moon and the spacecraft using F-net on both objects, iterate their respective velocity and position vectors, creating a simulation of their respective orbits. We then experimented with the initial velocity to try and approach figure-8 orbit, but otherwise showed that both objects have a gravitational influence. So here's a quick video of the black hole orbiting our system of the planet, the surroundings of the black hole. P-axis is purple, N-axis is orange, F-net is blue. The calculation is pretty straightforward. We have this being done in GlowScript, but essentially at each iteration it's using this equation that we showed previously, plugging in the known values and calculating the mass of that time. And you can see this here, our initial conditions are given here. Here we're calculating momentum of the planet total. Here we're calculating the velocity momentum over the iteration. The change in momentum is equal to the net force. We can do that conversion here. And then from having the net force, we can then calculate for F-net parallel and F-net perpendicular, and then finally calculate the mass of the black hole. So the second part, modeling the spacecraft's orbit. The first system is the spaceship and its surroundings of the moon and the planet. The second system is the moon and its surroundings of the spaceship and the planet. And note that although a figure-8 orbit was not achieved, the perturbation at the beginning of the orbit and the spiraling shown here indicates that both the moon and the planet are affecting the spacecraft. So to create this model, we first set our initial conditions and the initial speed of the ship. We then calculate the distance to each object and then use the universal gravitation law to calculate the force of gravity from each object to each object on each other object, and then found the net force acting on the moon, acting on the ship. And then at that point, we then just use velocity and position update to update their position to model it. So our results, we found the mass of the black hole to be equal to 1.37456 times 10 negative 34 kilograms, and we successfully modeled the motion of all three objects for part 2. So as sources of error, in calculating the mass of the black hole, we do not account for the force of gravity from the planet, so the mass should be slightly different than our reported value. And the second trial, the length of each iteration affects the lower precision we can get with representing orbits. This errors will magnify over time. So analysis, difference between force and momentum. As we explored in the first experiment, momentum and force are not the same thing. While momentum can be defined as sort of inertia, defined as a product of mass and velocity, force is the change in momentum over time. So while both force and momentum have their own parallel and perpendicular components to the object's circular motion, it is the change in the net force that changes the momentum, not the other way around. And finally, as a what if there was an imaginary system of a black hole, a star, a planet, and a moon, if you wanted to predict the motion of the entire system, which would include your model, the model will need to include the net force acting on each of the respective bodies, which will be the sum of the gravitational force exerted upon it by every other body in the system. From there, velocity and position update iterations will predict the motion of the entire system with reasonable accuracy if given initial position velocities. And assuming orbits are stable, the dominant interaction for each object will be the next largest object. For example, the star's orbit will be dominated by the black hole, the planet dominated by the star, etc. Thank you.